Good evening, everybody. Welcome to the continuation of our October Café Scientifique. My name is John Willis, and I'll be your host this evening. Turns out I'm also going to be your speaker this evening. And all I can say is I hope none of you are here under false pretenses, expecting to hear about the Silent Genome Project. They unfortunately had to reschedule, and we all love coming here. It's great. Herman's love having us, so I didn't want to cancel, especially with a couple of days' notice. So I pulled a presentation out of my back pocket, and I hope you enjoy it with me this evening. I want to tell you a little bit about it. It's called Everything You Ever Wanted to Know About the Big Bang, but Were Afraid to Ask, right? And if any of you remember that, most of you remember back that far, that's my Woody Allen reference for the evening, right? And this is a presentation I give to middle and high schools around Victoria, and I give it a fair bit. I must give it about 4 or 5 times a year, and it's a fun presentation. It's accessible. I'm not going to go easy on you. You're not going to get the finger puppet version, right? This is all going to be proper Big Bang astronomy and this kind of thing. But the nice thing is, it actually turns out there's some cool props that you can use to motivate it. And a few years ago, I realized that it's really easy to kind of fall into this, what I call the old white dude problem, where there's just an old white dude standing in front of PowerPoint going blah, 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 blah. And it works as far as it works, but it's not going to set the kids' brains on fire, right? So I decided to write a completely prop-driven cosmology talk just to kind of challenge myself a little bit. But unless you go to middle or high school in Victoria, you're not going to see this, right? So I thought this would be a nice opportunity to kind of share it with you guys, right? So now it's going to look a little bit different, right? Because at the schools, it's really interactive. I'm getting the kids, you have to sort of warm the kids up a bit. So I have a series of questions written on bits of card that they would normally read out for me. I'm going to kind of hold them up for you and then repeat them so you can see what's going on, just so we don't have to and fro on the stage a little bit. And there's a couple of bits where I would have a stage full of children, and we could maybe manage it this evening, but I figure I've got my stand-ins, my stools are going to be my stand-ins this evening, right? We're going to work it that way. So with no further ado, because I tend to monologue on this one, I'm going to try and keep it to 45 minutes, okay? Let's see where we can get, all right? Let me grab the first question. All right, this is kind of my homage to Subterranean Homesick Blues. I'm going to kind of flick through these as we go through the presentation. So I don't know if you can see that. It basically says, what do I mean when I talk about the universe? All right, and I'll show it for the live stream at home. What do I mean when I actually talk about the universe? I guess that what I'm trying to get across is, what's in my mind's eye when I say that to you guys? I'm just going to put this guy up a little bit. All right, there we go. So just to help us get orientated to start with, we're going to start with a map, okay? And this is one way of representing our place in the universe, okay? It's a beach ball, right? But it's also a star map. And the way it works is you are at the middle of the map, okay? The very center of the beach ball. If I've got "you are here" written on my t-shirt. If I had "you are here" written on this map, it would be pointing right into the middle. That's where Earth is. And then what the outside of the beach ball represents, well, that's the night sky as we see it, okay? And it's cool, first of all, because when you stand on planet Earth, you only ever see half of it, okay? But as soon as we step away, you get to see the whole night sky. And you can see a couple of really big features to orientate ourselves. So we've got this nice luminous green band going round the middle, okay? That's the Milky Way. Now that's kind of useful because that's going to be the starting point for orientating ourselves. That's the galaxy we live in. Because when I talk about the universe, the picture I have in my mind is galaxies, okay? Now, of course, you don't see them with your naked eye. You can see the Milky Way, and what have we got here? If you're lucky enough to go to the southern hemisphere, there's a couple of little luminous green splodges that you can see from the southern hemisphere. Those are what we call the small and the large Magellanic Clouds, okay? Those are actually nearby galaxies of our own, but very small ones, okay? Everything else on this map pretty much is a star, right? And we're used to seeing the stars in the night sky, but we don't see the galaxies because the unaided eye is not sensitive enough. You have an eye that has evolved to help you chase deer and dodge lions, right? And although it would be great to have a really powerful evolutionary eye that could work in the dark as well, that has a high evolutionary cost, and we decided not to pay that. So we have eyes that operate very well in daylight and pretty well in twilight, but not well at night. We need telescopes to help us. All right, so now what I'm going to do is I'm going to try and give you a sense of what the night sky would look like if we could tweak your eyes. If we could make them just a little bit more powerful, what would you actually see when you looked out at the night sky? And what you would see is galaxies. And those are the building blocks of the universe that I'm going to be talking about. It's a universe populated by galaxies. And stars that we're all quite familiar with, well, they exist within galaxies. So stars are building blocks of galaxies. Galaxies are building blocks of the universe, okay? This is a cool book, okay? Now, what I'd also try and do with the presentations is you have to try and make the school children understand what the world was like before the internet. If you wanted to see a picture of a galaxy, right, in 1980, 1970, 1960, you wouldn't go to some old screen and Google galaxy and hit images. That wasn't available to us. So this is a really cool book that was produced for astronomers just before Space Telescope launched in the early 90s. And this was a reference guide of the photographs of the galaxies that the Space Telescope would study. And I like it because it's just huge format. Okay, let me show you a couple of pictures here. All right, here we go. So it's like this on every page. All of the local galaxies in the universe that you might want to study with the Hubble Space Telescope. And the Hubble Space Telescope, because it had such powerful vision, you need these big blow-ups because it would be zooming in on all the tiny details that you can just about make out. Now, the other reason why I show you this one is because I know how big this galaxy looks on the sky. And it's really cool. All you have to do is hold your thumb out at arm's length, close one eye, and blot out the galaxy with your thumb. Okay, if I'm standing at about the right distance, then the galaxy should be about the same angular size as your thumb. Now, if that's true for some of you, could you give me a nod or a check? Is it kind of right? So if you went out and you had these tweaked eyes we're talking about, and you looked in the direction of M33, which is up there with M31, Andromeda in the night sky, so it's a northern constellation, this is how big this particular galaxy would seem. You would see this wonderful pinwheel suspended in the sky, and you wouldn't see just one of them. You would see galaxies everywhere in the night sky. If our eyes were just that little bit more powerful, you would see a completely different cosmos, where you don't see just the stars in our own galaxy, you would actually see all of the galaxies beyond, in our local neighborhood, if you like. And so then I wouldn't have to explain to you at all what I mean when I talk about the universe. You just say, oh yeah, he means all those galaxies up there in the sky. But what we have to do now is imagine now going out on a nice, cold, crisp, clear evening, looking up at the night sky, and this is what you're going to see. You're going to see a universe of galaxies, okay? So that's the answer to the first question, what I mean when I talk about the universe. All right, but I promised you big answers to big questions, okay? I worked really hard on coloring these all in today to make sure they're nice and visible. Does anyone want to shout out what the next question is? That's right, how old is the universe? That's a pretty fundamental question. Actually, well, it sounds like if you're a school child and you say, 100 years ago, we didn't know how to do this, right? And the school child's going to look at you and say, yeah, but the dinosaurs walked the earth 100 years ago, right? We hunted, cave bears 100 years ago. So saying 100 years ago doesn't really, matter to people, to the school children. But I think it is important that about 100 years ago, we got our first real answer to this question. And it came from the galaxies. And we were able to answer it because of a really neat phenomenon of the universe. And that is all of the galaxies are moving away from us. There's a couple of exceptions. There are some nuances, but I'm going to give you the broad picture. All of the galaxies are moving away from us. And the rule that describes how they move is giving us the age of the universe. And that's what this next little piece is going to be about. I'm going to show you how the galaxies in the universe are moving and what happened, how that lets us work out how old the universe is, okay? So first of all, we've got to do some basic astrophysics. We've got to work out how far away these galaxies are and how we measure how they're moving from us. And I'm not going to tell you at all about that. I'm going to lay out some safety cones on the stage, and that's going to represent all of that astrophysics whereby we do those basic measurements. I just want to stick to the big picture tonight, okay? So let me just hand out or space out those safety cones. For a guy who moves around the stage a lot, not having my hands to hold the mic is really sort of capturing me at the front. I have to remember to return here. Okay, let's do some astronomy. It would be straight, but there's only so much space on the stage. This is the point at which I'd get the school children to come up, etc. But we're going to try and do a little bit of social distancing. You're enjoying your food and your drink. So let me get my stand-ins. All right, here we are on planet Earth. This is going to be our observatory on planet Earth that we're going to use to measure the galaxies. And what you've got to remember, of course, is, well, we live on planet Earth. It's a galaxy itself, right? So our reference point is a galaxy. And then I'm just going to get 3 more galaxies, galaxy A, B, and C. And I'm going to put them at the right place from us and tell you how fast they're moving away. I'm going to have a little bit of jiggery-pokery to do to get this all stuck on, but bear with me, okay? Let me do Galaxy A. All right. No expense has been spared today, I have to tell you. No expense of ingenuity. Let's see if this works. Okay. All right, there's Galaxy A. If I can do this quickly, then the Scotch tape is going to hold. All right. You kind of get it, right? Galaxy B. Let's put Galaxy B down. All right. And Galaxy C. Don't forget my beers there. All right, good enough. Whoops, Daisy. This is the other thing I can't do at a school, okay? Which is why I was pleased to bring you this presentation tonight. Only once, actually, they gave me a gift of beer after talking at a school. That was unexpected. And very welcome, just in case any of you are school teachers in the audience. All right, now how have I laid them out? Let me tell you the rule. If the galaxy is 2 times further away, it's moving away from us 2 times faster. 3 times further, 3 times faster. It's a really simple rule. It's wonderful. You don't need to write any mathematics on the board. 2 times further, 2 times faster. So, in terms of our safety cones, if we call this one 0, this one's at 2, this one's at 4, and this one's at number 6, okay? So then we're just going to have an imaginary tick of the clock, okay? And the galaxies are going to move, but according to that rule. So what do? The first one's going to move 1 distance unit in 1 tick of the clock. The other one's 2 times further. It's going to move 2 times. So it's going to move, let me see, 1, 2, 3, 4, 5, 6. Here we go. Not quite enough room. And then 3 times further, 3 times faster. So this one at the end, that's going to move 3 units in the same space of time. That's what we observe. It's a bit more fun when you're shuffling school children around the stage. You don't have to pick them up and move them. You can actually give them simple commands and they'll follow them, especially when the teacher's in the room, right? That's how the expansion works. The cool thing, though, the reason why we do this is because we can run the movie backwards, okay? So if I run the movie backwards in 1 unit of time, well, of course, everything ends up where it originally started. So that goes to 2, that goes to 4, and that goes to 6 here. So you kind of get it. This one's moving 3 units in every space of time, every interval of time. This one's moving 2, this one's moving 1. So that's run the movie back a little bit, but why do we have to stop there? Let's keep running the movie back and see what's going to happen, right? So let's run the movie back another tick of the clock. So this guy moves to 1. This one moves to 2. Oh, I just destroyed a couple of stars there. And that one moves to 3. Now, also I can do this without having to compromise social distancing, right? Because hopefully you can see now, well, I've run the movie back a little bit. What happens if I run it back another tick of the clock? Where are all the galaxies going to end up? All on top of each other. Actually, all on top of us on planet Earth, okay? So all of the galaxies, if you run the movie backwards, appear to be coming from a point that's centered on us. Now that might not be true, but that's what it looks like. The amount of time it takes them to do that, to run the movie back and everything to land on top of each other, well, that point when everything lies on top of each other, that's one definition of the Big Bang. If you run the movie back, it's the Big Crunch. But if you're running the movie forward, it's the Big Bang. Everything starts from a particular point, and it moves away from, let me use the word origin, where it started, in this predictable, simple way. 2 times further, 2 times faster. So what is that number? Okay, well, we have to run the movie back just under 14 billion years. And then all of the galaxies would appear to all lie on top of each other, and that is one way that we can define what is the Big Bang. So the universe, according to that definition, the other definitions all agree, I should say, is just under 14 billion years old. How on earth do you explain the concept of 14 billion years to a 10-year-old or a 12-year-old? Actually, it's no, and this is what I tell them, it's no different for a 49-year-old or any age, right? I have no physical intuition that tells me what that age is. I'm an astronomer, my language is mathematics, I follow the mathematics and the implications it gives me, but I have no sense of what that means. I can provide you with a couple of waypoints, though. I can show you a couple of objects, right, like GPS waypoints, that will take us back part of the way. And it's cool to see how far you can get with actual objects you can hold in your hand that take you back to that seemingly impossibly distant time. So let me go and jiggle around back here and see what I can dig out, okay? All right, I'm going to pass these round so you have a chance to see them, but I'm going to describe it to you first and start passing it round. This is a piece of, well, it's fossilized mud, right? It's slate or mudstone. And this particular piece comes from a quarry in Utah. And if I look at the ages of the rocks above and below this particular piece of mudstone, it gives me an age of about 530 or so million years, 500 million years old, okay? Now, a piece of fossilized mud by itself is not that interesting, unless perhaps you're a geologist. What is interesting is there's a fossilized trilobite in here as well that's about the size of my pinky nail, okay? And at the time, this was one of the most advanced forms of life on planet Earth about 500 million years ago. We've got to work a bit harder to go back 14 billion years, but that's our first waypoint, okay? If you want to see them for yourself, and there's two different ways to see them. You can either jump in the car and drive all the way out to Field, BC, and go to Yoho National Park, and you can actually hike up to quarries that were used by scientists on the mountains there, where there are fields and fields of trilobites from this approximate geological age, about 500 million years ago. Some of you may have heard about it or read about it. This is the Cambrian explosion. This is where, when you look in the fossil record, you suddenly see a great proliferation in the diversity and abundance of life. And by diversity and abundance, we mean trilobites. That's one example of the Cambrian explosion. This didn't come from Yoho National Park. Let me tell you that. Otherwise, I'd be facing a $20,000 fine, okay, for removing a rock from a national park. You're going to love this. This came from a U-Dig quarry in Utah. And if you're driving past, you can drive up, park, pay your $20, get some safety glasses, some heavy gloves, and a chisel, and you can go and have 2 hours of fun in the quarry smashing up these mudstones, okay? And it's wonderful because of the way they form in layers. Like, it's a stone book. And every page you open hasn't been opened for over 500 million years, right? If you can't travel to Utah, this is what my wife discovered for me. This was my birthday present. 30 pounds of rocks arrived in a prepaid US Postal Service, slightly battered box, right, at my doorstep. And I then spent an afternoon on the patio opening these guys up. So this is basically from my box of rocks. Anyway, I'm going to hand this round. This is your 500 million year waypoint, okay? But we need to get further. Okay. Now, at some level, let me explain a nuance here. At some level, all of us are just under 14 billion years old. We are made of nuclear material, right, subatomic particles that were created in that Big Bang. I'm not going to go into how, but they were created there. Now, of course, those subatomic particles have had a wonderful journey through stars and multiple generations of stars to make all of the interesting atoms in us. So when I say something is a certain age, I mean it hasn't changed its form in that interval of time. So since that trilobite died in a mudslide, a submarine mudslide, it basically hasn't changed its form as it's fossilized. You can see its physical form. So the challenge is not just to, because all of the atoms are 13 billion years old or so, the challenge is to find something that's truly old that hasn't changed its form. All right, let's up the stakes, okay? This is 4.6 billion years old, okay? This is an iron meteorite. This took its form in the early stages of the formation of our solar system. This was basically a planet that didn't make it. It was a protoplanet that assembled enough mass to get hot in the center so that iron would melt and sink under its own gravity to the center of the protoplanet. But it did not last. Something else hit it, broke it into chunks. Those chunks floated around the solar system for about 4.6 billion years minus a little bit, okay, until they crossed the path of Earth's orbit and fell to Earth about 6,000 years ago in northern Argentina, okay, where they were used by the indigenous peoples there to make, tools, implements, weapons, this kind of thing. Not all of it. There was probably about 10, 20, 30 tons of material fell in this meteorite. So there was, some bits left over. When the Spanish arrived and they've heard about these stones that fell from the sky, they called the place Campo de Cielo. field of the sky, right? Field of heaven, if you like. And that's the name of this meteorite. This is a Campo de Cielo meteorite. It's been cut in half because it's really cool. You can see two things. One, it looks like little bits of iron, like Play-Doh, have been stuck together. That's how they basically formed and melted together in this protoplanet. If you know what you're looking for, you can see essentially the iron is forming visible crystals. I'm not going to give you a whole geology thing, but you can see there's shapes in the iron. That tells you the iron cooled very slowly. That's the number one thing that tells you this is not terrestrial iron, because all of the iron close to the surface of the Earth cooled very quickly when it erupted. Okay? This cooled over timescales of tens, hundreds of thousands of years. So that's how I know that I didn't waste my $1,000 in buying this meteorite. Okay? People say, well, I think it's great value for money. It's heavier than an iPhone. It's going to last longer than an iPhone. It does more interesting things than an iPhone, as far as I'm considered, right? And yeah, so I'm going to pass this one round. It's not fragile, right? Just don't drop it on your foot or the table, right? But this is a lovely piece, so enjoy this one. All right. That's as far as I can take you back, at least with something that's kind of easy to hold in your hand, right? So we got back 4.5, 4.6 billion years. So we can get back about a third of the way to the Big Bang. But that's interesting in itself, right? Because it tells you the age of the solar system is about 1/3 the age of the universe. We're not a momentary afterthought. Right? The evolution of planetary systems, the evolution of life has been going on for a big chunk of the age of the universe. Right? That itself is a very interesting idea. All right. One I can't enjoy too much. I've got to keep going with the questions because we're only on number 2, okay? All right. Let's see how good the eyesight is. Right? Let's. Okay. Who fancies shouting out this one? Where is the center of the Big Bang? And bonus marks, what are we expanding into? I just told you all of these galaxies are moving apart. Now, there's always a point at which you catch yourself and say, where's the center of the Big Bang? I thought everything was moving away from us. I thought I just told you that. Everything's ended up back on planet Earth. Well, that's one way it looks, but there's a different way of looking at it. Okay, and it's really cool. You can either do it with 2, 3, or 4-dimensional curved geometry mathematics, or you can do it with a really big balloon. And it's the same. I'm not hiding anything from you. It's not the finger puppet version. So let me get my big balloon. The kids love the balloon, right? Because of course you can't just bring into a classroom regular size balloons, right? You have to get jumbo balloons, right? I always have to check, does someone know CPR? Yeah, you laugh, right? Okay. Is it big enough? No. All right, yeah, we're good. All right, let's stick with this for the moment. Now, let me give you the real deal. Why have I got a balloon? Well, what I have here, the surface of the balloon is a curved 2-dimensional surface, right? I think we all understand that. Now, what of course is different is you're existing in 3 dimensions, so you get to see the balloon from outside. But we have to imagine we live on the surface of the balloon. We are 2-dimensional people, and this is our world. So what I'm going to do now that we've got this model of our universe, I'm going to draw these galaxies that you've already seen on our universe, and we're going to see how that expansion law translates on the surface of the balloon, okay? This is my special non-sharp Sharpie to not pop the balloon, okay? Now, things you learn, right? You'd think when you get a school child up to the stage and you say, could you draw a tic-tac-toe board on here? You figure you're going to talk the same language. Not always. Mostly, but not always. There's one point where the person didn't know what a tic-tac-toe board was. And then one of their colleagues at the back of the class shouted out, draw a hashtag. Okay. All right. There's our hashtag, if you like. Now this essentially, this is just like those safety cones I drew, I played with on the stage there. This is our coordinate system. This is how we're going to measure the distances between things. Only that. And let me just sketch on 3 galaxies. All right, so yeah, I win. Okay. Now let's imagine we live on one of these galaxies. Let me just draw an arrow there. Let's pretend we live on that one. All right. Now I'm going to run the movie forwards. I'm going to let the universe expand a little bit. Hopefully, I'm going to orientate the balloon so you can see what's going on, and then I'll explain what is being shown if it's not clear to you, okay? All right, okay. All right, so let's make the universe a bit bigger. Let's run the movie forwards. All right. Would anyone like to guess what they saw? What did you see? From our vantage point here, did the other galaxies move closer to us or further away from us? All right, further away. Now, in the time it took me to blow up the balloon, this galaxy moved 2 times further. So if you do distance divided by time, that moved 2 times faster. You've just reproduced the same thing that we saw on the stage in front of us. That's called Hubble's law. We renamed it a little bit a couple of years ago to honor another person as well. So that's called the Hubble Lametro Law, okay? Now the important thing is here, all right, so expansion on this 2-dimensional surface replicates what we observe, okay? Now mathematically, you can add an extra dimension to this, right? But it makes it difficult to show you with a balloon, right? But in 2 dimensions, you get everything as it should be. The important thing though is, because the question is, where's the center of the Big Bang? So if you were fixated upon your position on the Earth, you would say, all right, that's the center of the Big Bang. But I think you can all see, this is the wonderful thing about this demonstration. If you lived on this galaxy instead, and were looking back at our home in the universe, as this balloon expanded, you would that inhabitant of that distant galaxy would see us receding from them. They would see the same thing. There's no privileged position. And so the answer is, and if you were in this middle one, you'd see both of the galaxies moving away from you. So, and this is what I ask the school children. If I ask you to point on this balloon and say, where's the center of the Big Bang? They sometimes say, oh, it's the middle of the balloon. Well, I just told you that's against the rules. You've only got 2 dimensions to play with. You can't go to the middle, right? You can't stand outside of it. Some people say, oh, it's where the air goes in. Well, that's just where the air goes in. We can ignore that, okay? We have to imagine a perfect balloon that I can expand and contract. The actual answer is, where's the center of the Big Bang? Well, depends how you, is your cup half full or half empty? Because it's either everywhere or nowhere. Everywhere, well, everywhere is the sense that if you had a time machine and you went anywhere in the universe, anywhere in the universe today, and you set the time to come back 14 billion years in the past, everything would be in the same place, back at that one spot. There wouldn't be anywhere else to go. The other way of looking at it is that there's no center. Well, what that means when we say there's no center, there's no preferred position. There's no special place you can go to, right? Well, remember there was the bonus question then. You say, okay, there is no center. It's like in the Matrix. There is no spoon, okay? The bonus question though, what are we expanding into? Well, this is another point where you might say, well, the balloon's just getting bigger in 3 dimensions, right? But if you lived on the balloon, well, if you actually lived on the balloon, you would say, well, nothing's getting bigger, the rubber's just expanding. The space between the galaxies is just getting bigger. Now, this is a great point because it's a modern discovery. It's an older prediction, but a modern discovery. You might look at it and say, so is space-time really like a rubber balloon? Surely that must be, you're pushing the analogy too far. Well, if I flick the balloon, you can hear just it resonate. And what you're hearing there are basically waves moving across the surface of the balloon. It's like throwing a stone into a pond and watching a ripple. If I flick it, there are ripples moving across the surface of this balloon. They're just at a frequency where you can't see them. You can hear them, because that's all a sound wave is. It's the air being pushed around by the ripples moving on the surface of the balloon. We observe that. We can see space-time ripple and bend. This is what a gravitational wave is. And gravitational waves were predicted by Einstein right at the very beginning with his general theory of relativity, 1915, 1916. He predicted the existence of gravitational waves. It only took us 100 years to catch up with him and actually detect one unambiguously. And what we detected was two black holes merging with each other, and the effect of that merger is basically me doing that. And we detected the ripple moving out through the surface. Right? So the idea that space-time is a real thing, like the rubber on this balloon, sorry, I'll stay close to the microphone, it turns out our observations support that. That's one of the most wonderful things about fundamental science. You don't get to make up your own ideas. Nature tells you what is out there and what is not out there. We have to sometimes spend a lot of time working out exactly what nature is telling us. But these outlandish ideas, we adopt them because our observations of the universe tell us that's the way it is. And you just have to get your head around it. Now get used to it because there's a few more of those ideas coming, okay? All right, that was question 3. COVID means I can't let this go bounce around the classroom like I normally do, right? So that's why I have to be boring and hold on to it. All right, 37 minutes. Let's pretend I had 5 minutes for the introduction. I've been going for 32 minutes. I've got through 3 questions. I've got 3 more to get through, okay? So, next one. Here's another one. So you've got how old is the universe? How big is the universe, right? These are the questions, right? How old, how big, what's it made of, right? That's what we're going to try and answer. I always remember at this point that I shouldn't have let the balloon deflate, okay? You know, I've never had one explode, and it makes me think I'm not pushing them far enough, right? I mean, as an engineer, right, it's basically telling me I haven't done a destruction test. So let's see. No one's on a pacemaker here, are they? Bigger? All right, okay. Yeah. I'm a red giant after blowing up this. All right. Let's not use the hashtag side, okay? Let's now mark where we are in our two-dimensional universe, right? Let's just put a little cross there. You are here, all right? Now I'm going to try to draw a circle around that cross. Okay. That circle represents something imaginary but very important. Remember I told you the universe is just under 14 billion years old. In 14 billion years, well, we all know how fast the speed of light is, right? 186,000 miles per second, or 1 light minute a minute, 1 light hour an hour, 1 light year a year, okay? So in 14 billion years, light is going to travel 14 billion light years, all right? So let me draw on there. That's 14 billion light years away from us. So within that circle, there has been enough time in the age of the universe for light to travel from the edge of that circle to us. What lies beyond the circle, we assume that that line is just imaginary. There's plenty more universe out there. It just hasn't had enough time to get from there to here. Now, there is a nuance, because if you go and Google this right now, you're not going to get the answer 14 billion light years. The 14 billion is the number you'd get if the universe is not expanding. But I already told you the universe is getting bigger. So in that period of expansion, there's been a stretch of a factor of 3 that comes from looking at the mathematics. So the actual distance here is 42 billion light years. But I always tell people 14 because it's based upon simply the speed of light and the age of the universe. So what's beyond there? We don't know. The universe is certainly bigger than that. We don't see any edge, okay? It could be infinite, right? We don't know how big it is. And this is probably the most important answer that I give to the school children, because they expect old white dudes to stand up and know everything. That's kind of the way they see things work in the world. It's important to tell them, actually, there's very basic things we don't know. And being honest about what you don't know is the first step you have to take to answering those questions, okay? So how big is the universe? Well, you've probably all heard this phrase. The observable universe is everything in that circle. The actual universe is bigger, and we don't know how big, okay? All right, I'm going to be concise here and not explore that one further because I've got to do 2 more questions if I'm going to stick on time, okay? Oh, thank you very much. It's now a good point to tell you this is radioactive. I mean, that's how we know the age of it. It's by radiometric dating, right? I always have to do that because then I can tell you it's about as radioactive. Actually, a banana is more radioactive than this meteorite. Okay, you need very sensitive equipment, but it's radioactivity that tells us how old it is, okay? All right, question number 5. How am I doing for time? We're gonna get through it, but this is gonna be a bit faster. What kind of universe do we live in? Even ask. This is why I love just asking the questions, because they make you stop for a moment and go, there's different kinds? Actually, even within expanding, there's different kinds of universes. What is also neat is that we can answer that question. We can even work out there are different kinds of universes and work out what kind we live in. Now, a lot of what we use that I've told you about in this talk so far is all based on gravity. So let's go back to where gravity began. I like to ask the school children, who invented gravity, right? Isaac Newton, okay? Well, let's go back to Isaac Newton. I used to have an apple, but I dropped too many apples. And bruised apples just get messy really quickly. So this is my apple substitute, okay? Gravity is another thing that you don't actually need a great deal of mathematics to describe. We all know one basic thing about gravity. What goes up? There we go. All I want to do is I want to draw that on a graph. Whoops. What goes up must come down. So let me draw it first, and then I'll. Now, that's a little bit better. Let me draw it, okay. All right. You'll have to forgive my handwriting, right? What we have there, on the y-axis, the vertical line, that represents height above the floor. The x-axis, sorry, I'm standing in front of it. The x-axis represents time. So when I throw, this is the limit of my juggling skills right now. All right. That is what that looks like on a graph of height versus time. What goes up must come down. Now we're all used to that. Now, we live in the space age, okay? We know what happens if we were to throw this a little bit faster. If we threw this really fast, straight up in the air, with enough force to escape Earth's gravity, it would slow down a little bit, but then it would escape Earth's gravity and just coast out into the space in the solar system, all right? We can also draw that on this graph. It's just going to get further and further away with time. So it goes up, 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 and it just keeps on going, way off the top of the graph. If I threw this at just the right speed, at just the right angle, it wouldn't come back to Earth and it wouldn't fly off into space. It would go into orbit around Earth, okay? Now, to do it with one throw, you have to aim it really well, and it's very gently going to glide into an orbit, okay? But if I threw this at just the right speed, it's going to go into orbit, okay? The link with the galaxies is, if I draw the distance between the galaxies as a function of time, they also, in our universe, fit into those three cases, okay? Now, whether we know how fast they're moving, so whether they fall back, stay at the same distance, or get further away, depends upon how much mass, how much material is in the universe. So when I talk about the expansion of galaxies, I've just talked about what we measure today. But if we can look at galaxies in the past, we can measure what this curve looked like in the past and work out which one we might be on. Okay, we look at not the expansion of the universe, the expansion history. That's the great thing about looking back in time out there in the universe. Because of the finite travel time of light, every time you look beyond our galaxy, you're looking back in time. If you look to one of our closest galaxies, Andromeda, the light you're seeing from Andromeda is 2.2 million years old. If you go further and further and further, you're seeing older light. So you get that time travel effect for free. This is where it gets cool. This is another moment where nature pulls one on you. So I've told you, all right, what goes up might come down, it might fly off into space, or it might just slow down slowly forever. When we look at the past expansion history of galaxies, what we actually see is it goes up, it gets slower, and then as the height above the floor, the distance between galaxies gets to a certain point, something wonderful happens. It gets faster and faster. It's accelerating. It's as if, well, let me, use plain language. It's as if there's a magic force that we don't know about that's pushing the galaxies apart, okay? And what we've learned is we live in a universe not just that's expanding, the rate of the expansion is getting faster. We don't know why. It's one of the other wonderful discoveries. We've got to stop making these discoveries where the answer is, what is it? I don't know. Isn't it fantastic? I'm going to be in a job for the next 100 years, right? This is what they tell the school children, right? I'm telling you the things we know today. Your job is to stand up at the end of your career and tell us what we've learned in your lifetime, where we've made advances. Now, so we live in a very particular kind of universe. Now, before I go into more detail on it, I'm going to go on to the last question because it's related, and I don't want to go on too long, okay? This is the last of the biggies. We've had how old is the universe? How big is the universe? What is the universe made of? Okay, now I try to answer this at the end because it's only once we've seen the expansion history of the galaxies that we feel able to answer that question, okay? And it's another one of these wonderful questions where you look at me and you say, well, I can see what the universe is made of. It's made of tables, chairs, humans, beer, wine, air, planets, solar systems, stars, galaxies. Surely that's what the universe is made of. Partly, okay? Now, hopefully, most of you know that the atoms of which we are made are arranged in a pattern. We can understand that pattern. It's the periodic table, okay? That describes all the atoms that we know about in nature, okay? How many of you have seen the periodic tablecloth? Okay. Isn't the internet wonderful? right, you've even got it the right way up. So here is the periodic tablecloth. This is what we are used to encountering in the universe, okay? It turns out, though, the universe contains more than this, right? And we don't know exactly what it is, but we can put numbers on it. And that's what I'm going to do when I answer this last question for you. So we're going to find out how much of the universe is made of this good old atomic stuff we're used to, and how much is made of the problematic material that we've discovered, but we don't know what it is, okay? I'm going to have to draw something else on the board here, okay? I need 100 squares, okay? All right, those 100 squares, they represent the stuff we know must be in the universe from the answer to the last question. What kind of universe do we live in? We've looked at the expansion history of galaxies. It tells us how much stuff there is. And because of that weird behavior of the galaxies actually moving apart faster and faster, we can guess as to what the properties of that material is. But we're going to start with the atoms, okay? All the stuff you can see, okay? The stars, the galaxies, this kind of thing. That's it. All right, let me take this. All the stuff, all the atoms you can see easily is about 1/3 of one square. Now immediately that's a point at which you think, that's not much at all, really. What kind of impression do we have of the universe? Well, this, if nothing else, this gives you the scale of what has been learned in the last 100 years. It's those other 99.7 squares. Now, I told you, the atoms that are easy to see. What about the atoms that are difficult to see? That are very hot or very dusty or these kinds of things, or in stars that are very dim? That takes you up to 3 squares. That's all of the stuff on the periodic table spread through every galaxy, the space between galaxies, all of that. Let's go for another color. There is material in the universe that still has mass, but it doesn't play by the rules of normal atoms, right? Now, length of the talk isn't going to allow me to go into that, but I'm sure you've all heard of that. It's what we call dark matter. The name is scientifically chosen very carefully. It's matter because it feels the force of gravity. It's dark because we don't know what it is. You'll see this pattern repeat itself. Don't know what it is, call it dark. Okay? It turns out there's a lot of that. And not knowing what it is kind of interesting. So there you go, 27 more squares. We're up to 30 squares. So 1/3 of the universe is made of stuff that feels the force of gravity, but only a fraction of that is the normal atomic matter we're used to. And no one knows what it is. We have no shortage of ideas. One of the hopes for, expanding perhaps a facility you've heard about, the Large Hadron Collider, is that we might get to the sensitivity where we might detect a fundamental particle that is the dark matter, but we don't know what it is, okay? But we do have some theories. That's a good starting point. Now, that was where we stood about 30 years ago. Then we made this wonderful discovery that we looked in detail at the motions of galaxies, and we found out the expansion of the universe wasn't slowing down. It was speeding up. And to really, the best way I can explain to you how astounding that is if you were to do just that with the tennis ball. Throw it in the air, and you're used to what goes up must come down. And it doesn't do it. It just gets faster and faster and faster. And it was Arthur C. Clarke who said, any physics that we don't understand, we call magic. Okay, it must be some kind of magical force. It's not, it's simply an aspect of the universe we don't understand. But you can probably have done the maths the same way that I have here. if we've got the numbers right, it's accounting for 70 squares. It's not material, it's not like gravitating matter, it's more like an energy. So of course, what do we call it? Dark energy, because we don't know what it is. Now, I tell all the students, school students, my cosmology students, don't be fooled that we've given it a fancy name that we know what it is. I could call it fairy dust, I could call it unicorns, right? The mathematics wouldn't change, my knowledge of what it really represents would not be any different. Okay, just because we've given it a fancy name doesn't mean we know what it is. It's really the challenge. Most of what I've told you about covers the last 100 years of cosmology. The challenge, however long it may take, is to understand, among other things, what's this dark matter, what's this dark energy, and what does it have to do with gravity that we don't currently understand, right? That's where we think this is going. All right. I just about brought it in on time. Thank you very much for joining me, and we've got some time for questions if you would like. All right. Oh, let me just say, I have a meteorite. Is there a lonely trilobite still kicking around somewhere? Okay. Thank you very much. I'm lost in the glare. Oh, you had a question?
Yes. Where does antimatter fit in that graph?
Oh, yeah. Antimatter fits in here. Okay. It's normal atomic matter. It's just there's almost none of it occurring naturally in most parts of the universe today. We can make it in colliders, this kind of thing. But most of the universe is made of normal matter. But if you made more antimatter, it would fit in there. Okay. You have a question there.
One of the most romanticized notions of science that keeps bringing me back to these types of things is the acceptance of the idea that at some point the prevailing theories of the current age can be upended, but the belief systems of that day have to be thought of, to be rethought. With the coming release of the James Webb Telescope and the recent discoveries of the polar hexagon in the North Pole of Saturn, and the James Webb Telescope's ability to see deeper bands of light, and also the coupling of the discovery of electromagnetic fields, which are providing a better explanation as to why galaxies are held together. Are you excited by the prospect of this new sense of seeing in the next coming decades, and how that might affect the prevailing theories of the current age?
Yeah, let me try and paraphrase that quickly. So the question was basically, I guess it has two parts. One is, no theory is built to last, right? Every theory is always going to be replaced with something new, right? Something better, we hope, based upon observational data. And yes, something like that we believe is going to happen here, right? And we're actively looking for it. The issue is there's so many possibilities. Now, of course, the way you resolve among those possibilities is to look more at nature, right? Observe more. And yes, there's a lot of new toys coming online. And actually, there's a rule in I guess in all of life, but in astronomy as well. You don't get better doing what you're good at, right? So James Webb is really interesting, okay? But it's taking what we already do and it's making it a little bit different. If you actually want to ask me what really excites me, it's completely new ways at looking at the universe. That I think is because that's, as soon as you look in, you start doing something you're not good at, you're going to get better. And as you learn how to see better, you're going to see more things. And the best example of that is the discovery of gravitational waves, right? No electromagnetic, no radiation, no light whatsoever, but it's a new way of looking at the universe, completely new. And so, what we've always seen through the history of exploration, discovery, is if you look in a new way, you're going to see new things, right? That's almost a truism, right, of nature. So that's what I think is really exciting. Yeah. All right, you've been very patient. You've borne with me through this. Thank you for being a great audience. I will see you again in November. That concludes our October Café Size, and so watch out for the emails, and we'll be advertising everything, and I look forward to seeing you all again in November. Thank you very much.